Dear student, warm welcome to NPTEL 2 video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J.N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course Geosynthetics Engineering in Theory and Practice. This module 6, lecture 28, Geosynthetics for Reinforced Soil Retaining Wall. Now I will address recap of the previous lecture which I have covered design factor of safety based on mode of failure, ultimate limit state and serviceability limit state. External stability under static loading, external stability under seismic loading and internal stability. Earlier we talked about to calculate the embankment length LE by the pull-out test. Now alternatively LE can be expressed as for FHWA 1998 where LE is equal to SB into sigma H S Fs pull divided by twice sigma V CR F star alpha, where F star is the coefficient of pull out interaction between the soil and geotextile, alpha is scale correction factor. F star and alpha for standard backfill material except uniform sand with coefficient of uniformity Cu less than 4. So here typical type of the reinforcement, this is the default F star and default alpha. If it is a geogrid, so default F star value will be 0.8 into 10 pi. If the default alpha value is 0.8 and if we adopt geotextile, then default F star value 0.67 10 pi and default alpha is 0.6. So factor of safety for pull out should be 1.5 and minimum embedment length should be 1 meter. So here if you know that what will be the default factor F star and alpha value, here you know the coverage ratio and then sigma H is known, SB is known, sigma V is known, factor of safety against pull out known. So you can calculate alternatively what should be the anchor length from this equation. But remember that minimum embedment length should be 1 meter. And factor of safety against pull out you can consider 1.5. The anchorage capacity of the reinforcement per unit width P can be expressed as P is equal to twice LE sigma V CR F star into alpha. So P greater than equal to factor of safety for pull out into T of maximum. T maximum will be equal to SB into sigma of H. SB is the spacing between the reinforcement. For wraparound face wall, geosynthetics overlap length which we call L0, it also can be expressed as L0 is equal to SB into sigma H Fs pull divided by 4 of sigma V into CR F star into alpha. So this is the minimum value for the overlap L0 is equal to 1 meter. I am showing that what do you mean by the overlap of this geosynthetics material. When we will use the oven or non-oven geotextile material, so we have to overlap like this distance which you call the overlap, that is L of 0. Okay. You can construct this wall like this. So this is the geosynthetics material. open or non-open. So, you place this geosynthetic material like this and then you can wrap it. So, this distance is L0, which we call the overlap distance, and this is the length of the reinforcement, that is L, and this is the spacing between the reinforcement, that is which we call S of B. So, you know what you mean by overlap length. So, this overlap length can be expressed as this. So, if you know the L0, then you can calculate that, also you know that what will be the spacing and length of the reinforcement. Now, see connection strength. For long term creep and aging, consider a factor of safety is equal to 1.5. One connection testing for geosynthetic rupture, Simak et al. 1993, Elias and Christopher 1997, is given this equation that TAC, that means maximum connecting strength, should be less than equal to T of S, that means seam strength as per STM D4884 for seam testing. This divided by this reduction, this is the RFD, that means durability reduction factor for chemical stress cracking, thermal oxidation and hydrolysis, and this is RFCR, that is reduction factor for the creep, and this is 1.5 for long term creep factor of safety, consider 1.5. So, it should be that TAC, that means maximum connecting strength, should be less than equal to the TG divided by all this reduction factor, where TS is equal to seam strength. So, it should satisfy this criteria for the connecting strength. Now, connecting testing for pull out resistance of geosynthetics, as Elias and Christopher 1997, the maximum connecting strength can be written as TAC less than equal to TP by 1.5, where TP is equal to maximum pull out load per unit width of the reinforcement, or the pull out load at maximum deformation of 20 millimeter, whichever occur first. So, this is also important, that what maximum deformation you can take. You can take the deformation up to 20 millimeter, or you can say that what will be the maximum pull out reinforcement from the unit width of the reinforcement. So, whichever will occur first. So, accordingly you can calculate that what will be the maximum pull out force TP. Now, for internal stability check for seismic loading, the location of the maximum tensile force line does not change due to the rupture of the reinforcement or pull out force during the seismic loading. We are assuming that maximum tensile force line is the same as in the case of the static case. So, breakage failure, there is a possibility for basic failure due to the static case and due to the also dynamic case. For static case, T of maximum static should be less than equal to T allowable into CR divided by reduction factor. For dynamic case, T maximum dynamics should be less than equal to T allowable into CR divided by 0.75 into reduction factor. If it is a pull out failure, so T maximum should be less than equal to T P pull into CR divided by 0.75 into FSP, and T maximum should be less than equal to P pull out into CR divided by 0.75 into 1.5, or less than equal to 2 into F disturb into alpha divided by 0.75 into 1.5 into L of E into sigma V into CR. So, F disturb is dynamic should be equal to 0.8 into F star in the static, and alpha is generally take 0.6 and F star and alpha is equal to pull out factor, that is the default value. Due to seismic loading, the overall stiffness of geosynthetics will decrease. So, damping and amplification may increase. Step 6, serviceability limit state for internal stability. So, there is a possibility for the lateral displacement of the wall face. So, you have to check what will be the internal wall deformation, or you have to check to determine what will be the settlement of the reinforced soil wall for external wall settlement. So, these are the serviceability limit for the internal stability have to be checked. Now, for any project you have to look for the cost benefit analysis. So, you have to consider the cost analysis. Here Koiner TL 1998 compared the cost of geosynthetic reinforced soil wall with various other retaining wall. The cost of geotextile is about 25% wall total cost as per Bell ETL 1983. In India, the cost of the geosynthetic reinforced soil wall is about 30 to 50% less than that of conventional gravity retaining wall. Generally, geosynthetics and accessories about 35%, panel and block facing and mold about 32%, labor 15%, and margin and profit about 18%. Now, this figure shows the relationship between the height of the wall and the corresponding the cost of the wall in US dollar unit per meter square. This is given by Koiner TL 1998. You can see different types of the wall. This is the gravity wall, creep beam wall, mechanically stabilized reinforced earth wall, metal wall. So, if you can compare, you can see that with the increasing the height of the wall, cost also are increasing. So, if you compare with all the kinds of the wall, whether it is a gravity wall, whether it is a creep or beam wall, or it is a mechanically stabilized earth wall using the metallic reinforcement, you find that mechanically stabilized geosynthetic reinforced soil wall is much more cheaper compared to any other system or the material. Material cost depend upon the following element, that is modular block or panel fascia, gravel as drainage material, geosynthetic material as reinforcement, it may be geogrid, it may be geotextile, it may be geocomposite. Also leveling pad, when you construct this reinforced soil wall, you require the leveling pad. Cost of the design, soil and geosynthetic testing, site preparation and site assistance, and under drain pipe, placement of the backfill. So, these are the required. Construction procedure for precast concrete face wall. Here geogrid is layered at the foundation soil. Here I am just showing this is the wall and this is the leveling pad and this is the foundation depth, this is foundation. So, if you want to improve this foundation, you have to provide a geogrid or the geocell material to improve the bearing capacity if required, and you have to provide certain embedment depth here, and this panel or the block which could be the wooden wedge for providing the batter, and this is the leveling part in which that precast concrete facing element will rest. This is flexible like a hinge, and then reinforcement will be on the other side. It can be resisted by the reinforcement. So, this is the geogrid layer at the foundation, how the foundation subgrade can be improved. Either is the number of the layer of the reinforcement or you can provide with the geocell also at the base, for geocell for the as a foundation matrices, and this is as a facing element. So, here also geocell as a foundation matrices is shown. So, this you recall foundation subgrade. Now, leveling pad, the main objective of leveling pad is to erect the facing element. It has to be erect the facing element. So, this is one that shown the leveling pad with dimension, what is the reinforcement bar or 8 millimeter diameter, or the reinforcement bar 8 millimeter at the rate of 50 millimeter center to center, and here the reinforcement element bar at 12 millimeter diameter at the rate of 50 millimeter center to center, and this is 500 millimeter, this is 175, 150 and 150, and this is about 200 and this is 150, and that this total is about 325. Then this main objective of the leveling pad is to erect the facing element here. You have to erect the facing element here. So, foundation soil you have to provide with this kind of the leveling pad. Now, plain the cement concrete or PCC 1:2:4 lean concrete is placed beneath the leveling pad to minimize the differential settlement. Leveling pad should be constructed continuously up to the 20 meter in length with a gap of 20 millimeter and curing for at least 24 hours prior to the placement of the block or the panel. So, here you can see the erection of the facing element. Here cast with M35 grade concrete, erection of the panel after curing for 28 days. The minimum thickness of the panel is 140 millimeter. The panel are square, rectangular, hexagonal, cruciform and diamond shape. Here you can see that how the sequence of the erection of the panel. You can see initially you have to place like this, half of the mold like this, then you can place the entire the facing element. Okay, this is something cruciform in shape. Then cruciform like this you can construct. Here it has been shown that sequence for the erection of the panel. This is also important, and that how you have to erect the facing element and what you have to place the geogrid material which will be connected with the facing element. Here the different panel dimension in the precast fascia. You can see that here maybe 0.4, then 1.6, then 0.4 meter, or it may be 375, then this is 750 and this is 750 millimeter, and this is about 1.5 meter by 1.5 meter, this cruci shape panel, and then you can connect this geogrid material here. This is 3.75, this is 3.375, this is 375 millimeter, and this is 750. So, you can give one layer of the geogrid material here, another layer of the geogrid material here, and then you place the another panel here. Then this is 375, then upper will be also 375. So, entire will be about 750. So, spacing is almost 750 millimeter. So, 750 millimeter, 750 millimeter, like this, the spacing remain the constant. Also, different manufacturers have come up with the different types of the prefabricated spacing element. So, according to their manufacturing process and the quality of the geogrid material, and sometimes you can see that there will be the spacing is almost the fixed, and sometimes depending upon the block also you can change the spacing also depending upon that what will be the thickness of the block, whether you are using the panel or you are using the block. So, here precast concrete modulus block after Bathory and Simek 1994. You can see that face length may be 200 millimeter to 450 millimeter, width is 200 millimeter to 600 millimeter, height is 150 millimeter to 200 millimeter, and weight of the block generally 250 Newton to 500 Newton. Here this is the block, and this is act as a facing element, and because there is a gap where you can fill up with the aggregate, it will act as a drainage material, and geogrid is connected with this facing element or this block. So, it depends upon if it is a 200, then your spacing is 400, if it is a 300 block, then you can have the 600 millimeter spacing. So, depending upon the size of the blocks and the design, you will be place the geogrid material with the facing element accordingly. So, facing butter is not less than 1 in 40, but 6 degree is preferable. When you will construct this wall, then you require some butter here, some angle. That is generally 1 in 40, but 6 degree is preferable, and most of the Indian project use the 6 degree as a facing butter. So, minimum M25 grade concrete should be used. The facing unit should be connected with the help of shear key, shear pin or shear lips. The spacing between the reinforcement should not be more than 600 millimeter. So, here you can see some standard design of mechanically stabilized reinforced earth wall after the FHWA 2009. Here is the coarse filter aggregate, this minimum with about the 600 millimeter for 300 millimeter block, and also the 1000 millimeter for 535 millimeter block, and this is the wrap with geotextile material, and this is the optional, that is 150 millimeter lean mix or concrete leveling pad, and this is the facing element. Here from this distance will be about 1200 millimeter, and here minimum about 600 millimeter. You require certain distance from here what the drain is out, this is minimum about 1200 millimeter, and then 1:3 or the flatter slope. You see here this is the facing element, and here is the facing element, and this is the wall better, it may be within the 6, and on the top of the facing element and the wall here is a cap, and this is the drainage swage you can provide with slope 3:1, and this is the number of the layer of the reinforcing material, or you can say it is the geogrid material, and in between you can provide with the geotextile material here, that may be woven or non-woven geotextile material, and inside this is the course of aggregate. So, at the same time also you require the drainage system at the back of the reinforced soil wall. So, this side you should provide with a kind of the drainage here with a certain angle, you recall from drainage, with a slope of 2 vertical to 1 horizontal. You can provide with the any geocomposite or geotextile material, and water can also, it can be drained it out through this. Placement of the backfill and compaction. This is important because you should properly place the backfill material. Sometimes if you do not properly compact the material and proper selection of the material, there is a possibility for the failure. So, the backfill material are compacted with a roller compactor to achieve at least 95% modified Proctor density. The lip thickness should not be more than 200 millimeter. The lightweight hand compactor not exceeding 75 kg should be used to compact near to the facing element. So, you can see sometimes when you will compact the one layer, then you fill up with the soil, and then you have to compact it, and you should maintain certain thickness between the geotextile and the soil. So, it should maintain that 200 millimeter or 250 millimeter, otherwise there is a possibility for the damage of the geogrid material. And when you are compacting, like if this is the facing element of the wall, and when you are compacting, that means this lightweight compactor, the lightweight hand compactor not exceeding 75 kg should be used to compact near to the facing element, and then vibroported compactor, it may be 1.5 meter from the edge of the facing element. So, within 1.5 meter facing element, you have to use the lightweight hand compactor and not exceeding weight about 75 kg. And beyond the 1.5, so you can use the vibroplate compactor, or maximum weight maybe 1000 kg should be used to compact with 1.5 meter from the edge of the facing element. So, no heavy equipment should be kept near to the face of the wall, because if you keep the near to the face of the wall, and there is a possibility for bulging of the facing element. So, it is to be careful when you will compact this reinforced soil retaining wall near to the facing element. So, it is very important that during the compaction, both horizontal and the vertical alignment of the fascia panel or the block must be observed regularly. Now, placement of the reinforcement. After filling and compaction up to the desired height, geogrid reinforcement is connected with the facing element and placed horizontally. So, for example, if you place here, compact it, after that you are placing this geogrid material here, and which geogrid material should be connected with this facing element and placed horizontally. So, geogrid should be placed in the machine direction perpendicular to the face of the wall. That means which direction the strength is more. So, you should not sometimes place the geogrid material in the cross machine direction, which strength is less. So, you have to be careful that how you are placing the geogrid material, whether it is machine direction or cross machine direction for the construction of the reinforced soil wall. So, you have to place the geogrid material in the machine direction, which tensile strength is more. Next, the drainage. Drainage is very important. Most of the reinforced soil structure fail or collapse due to the development of excess hydrostatic pressure at the back of the retaining wall. You can see if this is the wall, this is the reinforced soil wall, back of the reinforced soil wall, there is a possibility for development of excess pore water pressure, and if there is a excess pore water pressure, then there is a possibility for the collapse of the geosynthetic reinforced soil wall. That is why you should provide proper kind of the drainage system. Drainage is very important. So, you can provide with the chimney drain and the back of the retaining wall. In conventional, you used to 300, 400 to 500 millimeter thickness of the good quality of aggregate. Alternative to that, you can provide with a geotextile material, either woven or non-woven, or you can provide with the geocomposite material. So, this is very important. Koener and the Sung 2001 documented that 20 out of 26 mechanically stabilized earth wall fell either by excessive deformation or collapse. Therefore, proper design of drainage system is needed. So, this is the drainage using the blanket with the chimney drain after Colin ETL 2006. Here is the blanket drain, here is the chimney drain, and this drainage you have to provide about of 0.7 H. This is the leveling pad filled with the sand and gravel, and this is the segmented retaining wall, and you can see that you have to place the chimney drate at the back of the reinforced soil wall, at the base of the wall as a blanket drain, and this is the collection pipe. So, all the water can pass through this collection pipe, and also you can see that back of the facing element where you can provide with the drainage aggregate or the geotextile material. This is the segmental retaining wall, and this is the geotextile material. It should not be mixed with the backfill material in the reinforced soil zone. That is why it is provided with the geotextile as a filter, and with this aggregate, drainage aggregate, then water can pass through this collection pipe. Also at the top you can provide with a low permeability fill material, and on the top of that is the asphalt. So, water may, due to the rain, water may percolate through the asphalt, and it also can pass as act as a drainage and pass through the collected pipe. So, it requires the back of the retaining wall by providing the chimney drain, also at the bottom of the reinforced soil wall which will act as a blanket drain, and also that back of the facing element, this is as a drainage aggregate, and also at the top where you can provide with the low permeability fill material. So, this is important, that how you can use the different kinds of the drain to control the drainage system. Otherwise, most of the cases find there is a possibility for the failure of the reinforced soil wall. This is also another drainage system, and here you can see that particularly this here, and nowadays also drainage system you can provide with the geomembrane barrier for reinforced soil wall after FHW 2009. So, when there is a, if there is a wearing surface, and this is the base course and this is the aggregate, and here is minimum 0.75 millimeter of the geomembrane you can provide here. Also you can perforate it with the wrapped geotextile material. Then if you provide with the impermeable material, then water cannot percolate through this to the reinforced soil wall. So, the what here that geomembrane will act as a barrier, and then this should be drained out of this wall. So, it is also sometimes required on the top of this wall you can provide with the minimum thickness of 0.75 millimeter thickness of the geomembrane to control the drainage. So, water cannot percolate in that case. So, submission of material and test report by manufacturer. So, the contractor should submit the following information to the engineer: the name of the manufacturer, current full address, polymer type for geosynthetics, ion or fiber type for geosynthetic structure, roll number of geosynthetics. This is also important, because it should be known that what roll number has been sent to the site or to the laboratory for testing, and certified the test result. Now, design critique: the mobilized strain in reinforced soil wall may be relatively high because of the extensibility of reinforcement. It is recommended to use critical state shearing resistance angle instead of peak friction angle of the soil for design. That is Jewell 1991. At the end of the construction, the serviceability strain criteria for long design life of reinforced soil wall, 1.0% for the wall and 0.5% for bridge abutment. Most of the reinforced soil structure fail due to lateral deformation at the top and bulging of the wall. It is recommended to provide longer length reinforcement at the top, middle and bottom of the reinforcement. And for the remaining height of the wall, shorter length reinforcement can be used. We will show you some example, because most of the cases it has been observed the reinforced soil structure fell by the bulging almost at the middle, and sometimes due to the seismic effect there is a possibility for the fail at the top. So, you require proper kind of the reinforcement material or longer length of the reinforcement material at the top to prevent the kind of the seismic aspect. And also most of the cases as the wall fell as a bulging, so you can provide the longer length of the reinforcement in the middle, and also at the bottom, because there is an improvement for the bearing capacity, so you can provide the longer length of the reinforcement at the bottom, and in between you can reduce the length of the reinforcement or shorter length of the reinforcement can be used. We will give you some of the example that how you can most economical and stable structure design can be made, where we can use the coverage ratio value, whether coverage ratio value is 1 and coverage ratio value 0.6, and how you can save the geogrid reinforcement, how you can make more stable and economical design. So, this we will show you later with some example. Now, failure of the structure. The geosynthetic reinforced soil wall fell or collapse due to several reasons: excess hydrostatic pressure, excessive lateral deformation, improper selection of the backfill material. So, you have to be careful for the selection of the backfill material. You should follow up the specification and gradation of the material. Most of the time whatever you find the locally available material, you should not use it. You have to check whether that material is suitable or not, whether that material have satisfied the proper gradation or not. I have shown you earlier the different kind of the system, what will be the number of process passing through that material, whether it is 15%, 0%, you check and follow up. Because most of the structure also fail because for not proper selection of the backfill material, this is also very important. And local instability, distortion of the modular block or the panel. Most of the time that it is also very important to check the modular block or the panel whether it satisfies the local stability or not, because every block or the panel has its own weight, and you have to check for the shear moment and check that whether this is modular block or the panel is satisfying the local stability criteria or not. Then contractor lack of workmanship for quality control. This quality control is very, very important. It requires proper kind of the testing, proper kind of the compaction, it requires proper kind of the moisture content, what moisture content is to be added, how do you compact, whether it will achieve the required compaction or not. So, this is also very important, that workmanship for quality control. If you do not do proper kind of the work and proper kind of the quality control of the material, then there is a possibility for the failure of the structure. And also you have to check bearing capacity and deep-seated failure. So, you check the bearing capacity, you require that proper kind of the soil exploration in detail and check what will be the bearing capacity of the soil in that locality. If it satisfies, the whatever you require, then it is okay. If it is not, then you need to improve the soil. So there are, I mentioned different types of the system to improve the soil, and you check the bearing capacity. And most of the time also that you don't go for the deep seated kind of the failure or the global stability also failure. So this one has to be taken care and check that what will be the factor of safety against the global stability or deep seated failure stability. Because for the global failure causing the formation of huge heap in front of the fascia element. This kind of the problem also happen in India. You can see how kind of the heap has been formed in the front of the facing element, huge heap, because we do not consider this global stability. So you should check that global stability problem. No site specific design. Sometimes is only is copycat and the paste it, and also non-professional people also are providing with the design. They don't have the knowledge about the civil engineering. They don't have the knowledge about geosynthetic engineering. Sometimes they put it from here and there and paste it and sell the design with 30% less. You don't know what kind of the danger, what kind of the problem may occur, what kind of the failure may occur for this. So one has to be take care for this. Heavy compaction within 1 to 1.5 meter of the wall face. So you have to be careful for the compaction near to the facing element. I say that you should use the hand roller which weight is about 75 kg. If you go for the heavy compaction, then there is a possibility for the bulging. You don't know the reason why the bulging also have been formed sometimes. So you will require proper kind of the compaction. You should not go for heavy compaction within that zone. No outlet drainage provided for the internal drainage. You find sometimes there have been construction for the reinforced wall, but no outlet. You don't know the water can pass through. And the placement also of the pipe, you can see that you can check out the water level. So you check that from where it should pass the water through the pipe. So you can provide proper kind of the slope in order that water can be outlet from that zone. So sometimes you find there is no outlet, and then there is a possibility for the failure. And this reinforced soil structure fail due to tension failure. Then geogrid may be, I say, connection failure. There is a geogrid slippage or block wall failure. Block wall itself will fail. And sometimes also the placement of the block properly. Sometimes the block has been placed upside down, and it happened, and the structure collapsed. When you look nearer to the wall, you find the block has been placed upside down. So that was the reason that there is a possibility for the failure. Then poor attention to facing connection. So when you connect the geogrid material with the facing element, you have to see what kind of the connection you are providing, whether you are placing properly or not. And poor inspection. So sometimes nobody bother about, no engineers, no qualified engineers are there to inspect what is happening. And sometimes improper compaction. You require 90-95% compaction, the contractor finish with 80-85% compaction. So there is a possibility for the failure. And poor quality control and the assurance. You need proper quality control from the manufacturer's side, from the contractor's side. And inadequate design of the backfill slope and the foundation. You require the proper design you should follow some of the code and design standard, which we have also followed in this course, that is strength and input soil and other field, British standard in 1995, mechanically stabilized earth wall and input soil slope, design and construction guideline FHWA 2001, design manual for segmental retaining wall, that is NCMA design manual 1996, segmental retaining wall SIGMIC design manual by Dr. R.J. Rathures. So, you can follow the sum of the code and design standard. There are many different design standard. Individual country have their own design standard. So, most of the cases that we follow up this standard, particularly the BSI and the FHW, and then if you follow up properly, and then you will be successful for the design of reinforced soil wall. So, what we covered here, that for the reinforced soil wall, how to design and how you can place the geogrid material, what kind of the failure may occur. There may be failure for the sliding, there is a failure for the overturning, there is a failure for the bearing capacity, there may be failure for the deep seated or the due to the global stability. You require proper kind of the quality control. You require for the quality control from the manufacturer side, quality control from the contractor side. Also, you require proper kind of the design and proper kind of the selection of the geogrid material. Also, we have learned that what should be the embankment length or the anchor length of the design. So, if it is the anchor length design, how you can calculate that anchor length, how you can calculate the what will be the total length of the geogrid. Also, you can know that how to calculate the spacing between the geogrid reinforcement, that means spacing is the S of V, and also you have to check that what will be the connecting strength, when it is the seismic condition, when it is a static condition, and sometimes that structure collapse because due to the improper connection between the geogrid and the facing element. So, one has to be careful for the connecting strength. Also, it is required for the proper selection of the backfill material. So, it requires proper kind of the gradation of the material. If we wrongly select the backfill material, which will not satisfy the criteria. So, first of all, you have to check that what kind of backfill material you want to use for the construction site. So, you cannot use the any material as you like it, because most of the cases this structure collapse because for improper selection of the backfill material. Apart from this backfill material, you require proper kind of the drainage system. So, you require the drainage system on the back of the retaining wall, at the base of the retaining wall, and also at the back of the facing element, and also at the top of the reinforced soil wall. Now, it is also you can use the kind of the very minimum thickness of the geomembrane material in which water cannot percolate from the top to the bottom of the geogrid reinforced soil wall. So, these are the some of the important issue which we have to keep in mind, and also we will focus next that how you can design, means you can design more economical design, how the length of the reinforcement can be reduced, how we can place the reinforcement at the different zone or the different layer. As I mentioned that you can provide with the longer length at the top and also at the middle and also at the bottom, because you can provide with the longer length at the middle, because most of the cases it has been observed there is a possibility for the failure of the structure due to the bulging. To control the bulging, so you can provide with the longer length of the reinforcement at the middle of the reinforced soil retaining wall. And also due to the seismic aspect, and there is a shearing resistance can develop on the top of the reinforced soil wall, and that was the reason that you can provide with the longer length on the top of the reinforcement. And due to the foundation soil problem, if soil is not in good condition, so you can also provide with the longer length at the bottom of the reinforcement, and in between you can reduce the thickness, you can reduce the length of the reinforcement, so you can make a more economical and the stable design. You can also provide with the system like a cover ratio, that is C of R value. So, this also will reflect that cost of the reinforced soil structure. You can provide with the 60% of the geogrid reinforcement instead of 100% of the geogrid reinforcement. It may be 60%, it may require maybe little bit high strength of the geogrid material with respect to 100% of the geogrid material, but if you can think in terms of the overall cost and the quantity of the geogrid material, it may be the suitable or economical for the 60% of the geogrid material. So, we require proper design, proper selection of the material, and also installation technique. So, next we will discuss about the some example that how we can make use of the design with the different coverage ratio. With this, I ended up the lecture today. If you have any question, thank you for listening.